Good morning, everybody. Welcome to the NPTEL online certification course. The second module, lecture 4, is on biomechanics of the elbow joint. This was part 1 of the lecture, followed by part 2. The concepts covered in this lecture are the biomechanics of the elbow joint, the movements and degrees of freedom during flexion and extension, which is one of the primary movement of the elbow joint. And subsequently, we will be discussing about a problem on biomechanical analysis of the elbow. The part 1 of the problem will be discussed in this lecture, followed by part 2 of the problem later in a separate presentation. Let us revisit the structure and the joints of the elbow joint, which is constituted of the following joints: the humero-ulnar joint, the radio-humeral joint and radio-ulnar joint. A detailed lecture on the structure and function of the elbow joint was earlier discussed in module 1. We will be briefly discussing the structure and the movements in this lecture, which deals with the basic biomechanics of the elbow joint. The movements offered by the elbow joint are the flexion, extension and pronation, supination. So, you can see here the range of normal range of flexion is from 0 to 150 degrees, and the opposite movement is known as extension. From the neutral position, if we rotate the arm outward, then it is called supination. Rotating the forearm inward is called pronation. Now, we will be concentrating in this lecture on the major movement offered by the elbow joint, that is flexion, extension. Now, when a forearm moves toward the body by bending the elbow joint, which is shown by this, by bending the elbow joint, it is called flexion. The opposite movement, when we are straightening the arm, is known as extension. The flexion is limited by the anterior surfaces of the forearm and arm coming into contact with each other. The extension is limited by the tension of the anterior ligament and the brachialis muscle. The change in position of the center of rotation of the elbow during the movement, flexion, extension, either way, indicate that the joint cannot be truly represented by a simple hinge joint. Let us summarize the flexor muscles that contributes towards this movement, flexion. The flexor muscles, the main muscles are the brachialis, the biceps brachii and the brachioradialis. They actually connect the upper arm to the forearm. When they contract during flexion, they become shorter and pull the forearm towards the upper arm. So, the main muscles of the flexion are actually shown here in the presented in the slide. The anterior view can see the biceps brachii, the long and short heads, the brachialis and brachioradialis, here in the anterior view also. And in these two images, we can also see the three muscles very clearly. The elbow extension, on the other hand, is the extension of the forearm at the elbow joint. This is basically a movement which involves increase of the angle at the elbow to bring the forearm back to the anatomical position from a flexed position. So, from a flexed position, we are bringing the forearm back to the normal position, and that is due to the movement extension. There is one muscle involved in extension, that is the triceps brachii muscle. The attachment side of the muscle and the muscle orientation is shown in the posterior view as indicated in the slide. Let us now discuss an important angular measurement which is known as the carrying angle. This is the angle between the long axis of the extended forearm and the long axis of the arm. So, we have, it is the angle subtended between the long axis of the extended forearm and the long axis of the arm. It opens laterally about 170 degrees in case of male and 167 degrees in case of female subjects. However, it disappears when the elbow is flexed. So, in a flexed position, the carrying angle disappears. The carrying angle permits the forearm to clear the hips in swinging movements during walking and is important when we are carrying objects. Let us discuss about the motions offered by the thorax, shoulder, elbow, wrist complex. So, individually we have the shoulder complex, we have the elbow complex, we have the wrist joint. So, together it actually forms an important upper extremity complex responsible for large range of movements. Now, if we consider the movements of each joint, then we have 3 thorax rotation and 3 thorax translation with respect to a rigid frame. The motions offered by the shoulder joint, that comprises of the acromioclavicular joint, the sternoclavicular joint and the glenohumeral joints, are 3 AC joint rotations, 3 sternoclavicular joint rotations and 3 glenohumeral joint rotations. Each of these joints are spherical joints, and therefore, each joint offer us 3 rotational degrees of freedom. The elbow joint actually offers 2 motions. So, one is the flexion extension, the other is the pronation supination. So, we have 2 motions offered by the elbow joint. The last is the wrist joint, which offers 3 wrist rotation corresponding to 3 hand positions. Now, based on these motions, the degrees of freedom of the shoulder, elbow, wrist joint can be summarized based on the model proposed by the Delft shoulder group, and the model is quite popular and famously called the Delft shoulder and elbow model, proposed by Franz van der Helm group at Delft University of Technology. So, the degrees of freedom of the thorax with respect to the global coordinate system or rigid frame is in total 6, that it consists of 3 rotations and 3 translation. The sternoclavicular joint offers 3 degrees of freedom, acromioclavicular joint 3 degrees of freedom, and the glenohumeral joint 3 degrees of freedom, as discussed earlier. Now, the scapulothoracic gliding plane is modeled with the thorax as an ellipsoid, on which 2 points of the medial border are sliding. So, at these 2 points, 2 degrees of freedom are constrained, and that is the reason we put a minus before 2. So, it is 2 constraints offered by the scapulothoracic gliding plane. An additional constraint is applied by the assumption that the conoid ligament is rigid. So, additional degrees of freedom is constrained, leading to -1 due to the assumption that the conoid ligament is rigid. Now, this is mostly the shoulder complex with its degrees of freedom listed corresponding to each joint. If we now move to the elbow, as discussed earlier, we have 2 rotations. So, we have one about the humero-ulnar joint, the other about the radio-ulnar joint. So, we add 1 degree of freedom to each joint. The wrist, as discussed earlier, offers us 3 rotations. So, it has 3 degrees of freedom. Now, if we add all the degrees of freedom, the total degrees of freedom of the shoulder, elbow and wrist complex comes out to be 17. Now, let us move to the biomechanical analysis of the elbow. So, this analysis will be based on a solved problem. Before we define the problem, a few considerations need to be discussed. For the elbow joint, it is apparent that a dynamic analysis is not necessary. This is because heavily loaded movements of the joint tend to be slow. Hence, the following biomechanical analysis will actually neglect the dynamic effects, and we will be considering a problem on biomechanical analysis of the elbow, which is based on a static analysis. Let us define the problem. So, you can see that a subject is carrying a load of 311.25 Newton in the position of elbow being flexed at 90 degrees. Okay. So, elbow flexion is 90 degree. In this position, it is carrying a load in the hand, and the hands are in neutral position of rotation. So, it is not, there is no rotation like the pronation or supination, there is no rotation. So, it is in the neutral position of rotation. The biceps, brachialis and brachioradialis are the main flexure muscles acting to resist the external load. Now, in order to proceed with the problem, we first consider some assumption to simplify the analysis. The first assumption is that the forces imposed across the joint by the wrist abductors or the finger flexors, the muscles of the wrist or the finger flexors are not considered in the analysis. It is purely based on the muscles of the elbow. Now, the muscle forces that are acting on the elbow and considered in this analysis is assumed to act in straight lines. Now, let us first look into the two parts of the problem along with the aim of the calculation that is performed or undertaking in these two different parts. The aim of the calculation is to define the magnitude and directions of the force acting within the elbow joint. So, as a first step, we define the geometry and find the moment arms of the muscle activity about the joint axis. Then, in the second step, using these moment arms, we calculate the muscle forces. Rather, the muscle forces are estimated. And in the final third step, once the muscle forces are estimated, the ligament force and the joint reaction forces are calculated based on the output of part 1. Okay. So, the first two steps together make the first part of the problem that I am going to discuss in this lecture. The second part of the problem is much more complex and more elaborate. So, we will be taking up that in a separate lecture following this lecture. Now, the detailed geometry data of the problem is presented in the slide. The distance of the points of action of the muscle forces on the forearm from the joint axis A is given as the action of the biceps insertion on the radius is 0.38 meters from the joint axis A. Which is given here. The muscle brachialis is also located at a similar distance, but the insertion is on ulna. The brachioradialis muscle is insertion on the radius. So, it is located at a distance of 0.24, as you can see here, meters from the joint axis A. The limb weight of 32.5 Newton is assumed to act at the center of gravity, which is located at a distance 0.16 meters from the joint axis A. Finally, the load which is being carried of 311.25 Newton is assumed to be acting at the distal end of the metacarpals, and that is at a distance 0.35 meters from the joint axis A. Now, in continuation to the earlier slide, we present the same figure, but here we actually indicate the distance from the joint axis A of the points of action of the muscle forces on the humerus. So, we have brachioradialis muscle acting at a position of 0.065 meters from the joint axis. The brachialis muscle is acting at a distance 0.08 meters from the joint axis, and the biceps, for the biceps, a point on the line of action is defined by the location 0.20 meters out of the humeral shaft and 0.32 meters from the joint axis A. So, using this geometric data, we can define the lines of action of the muscles and hence calculate their moment arms about the joint axis A. Now, we are entering the calculations on the moment arm of each muscle. The first muscle we consider is the brachialis muscle. So, the moment arm of the brachialis muscle about the axis A equals to the length BD. So, BD is the moment arm denoted by LBR. So, considering the given geometric data, we can actually calculate the angle DAC as 64.6 degrees, considering tan of the angle DAC, the dimensions given, we can calculate the actual angle DAC. So, once we calculate the angle DAC, by similar triangle we can get the angle ADB, which is calculated as 25.4 degrees. So, the moment arm LBR comes out to be 0.034 meters as shown in the calculation. Next is the calculation of the moment arm brachioradialis. Following similar geometric procedure, we can actually calculate the moment arm of the brachioradialis muscle about the joint axis A, which is calculated as 0.063 meters. The calculation of the moment arm of the bicep muscle is indicated in this slide. So, it can be recalled that a point C on the line of action of the bicep muscle is defined by the data given in the problem. So, it is 0.02 meters out of the humeral shaft and 0.32 meters, 0.32 meters from the joint axis vertically upwards. So, we can locate the point C along the line of action of the muscle bicep based on the two given points. We can now calculate the moment arm LBI, moment arm of the bicep muscle, using simple geometry. The next step, rather a major step, is the estimation of the muscle forces. Now, in order to undertake the calculation for the estimation of the muscle forces, it is assumed that all the three muscles are stressed to the same intensity. Okay? So, if we consider this assumption, so if we consider the stress to be same in all the muscles, then the forces produced in each muscle will be proportional to its physiological cross-sectional area. The cross-sectional area values of each muscle has been found earlier by dissection, and the typical values of the cross-sectional area of the muscles are given here, as you can see. So, once we have the stress generated in each muscle, we can multiply the cross-sectional area with the stresses generated in each muscle, and then we get the forces. And if we multiply the forces with the moment arm of the muscle, we get the moments corresponding to each muscle. But before that, we first calculate the moment exerted by the external loads. The external loads are the applied load, so the moment is calculated by multiplying the load with the distance from the joint axis A, which gives the moment exerted by the applied load is as 108.93 Newton meter. Now, the moment exerted by the limb weight is also considered as an external moment. So, the limb weight is assumed to be 32.5 Newton, and it is acting through the center of gravity of the limb. So, we get a moment value of 5.2 Newton meters. So, we now estimate the moments produced by each muscle. So, the moment produced by each muscle, as I discussed earlier, is the stress in the muscle multiplied by the corresponding physiological cross-sectional area of the muscle multiplied by the moment arm of the muscle. So, for each muscle we can write individually the following expressions. Now, once we have calculated the individual moments corresponding to the muscles as well as the moments of the external forces, we need to balance these moments since the limb is in equilibrium while carrying the load. So, the moment balance about the joint axis can be considered. On the left hand side of the equation, we have the moments generated by the load and the limb weight. On the right hand side, we have the sum of the moments of the muscles, which actually balances the moment of the external load. So, this is a very important step in the problem where we undertake moment balance of the muscle forces and the moment applied by the external load. So, when we substitute the values of these variables here, we can calculate the stress in the muscle, and we had assumed that a muscle is stressed at the same intensity. So, this is the stress within the flexor muscles which resists the applied load. So, using this value of stress and the corresponding cross sectional area, we can individually calculate the muscle forces, flexor muscles, the muscle biceps, brachialis and brachioradialis. So, the values are calculated as shown in the figure. With the magnitudes and direction of these muscle forces, which are now known, the loading imposed on the joint itself can be estimated. The calculation of the ligamentous and more detailed calculations on the joint reaction forces will be continued in part 2 of this lecture. So, it is assumed that the radius and the ulna each carry a share of the applied loading equivalent to the strength of their muscle arrangement. Hence, the individual joint reaction forces, humeroradial and humeroulnar are due to the humeroradial and humeroulnar articulations may be found, which will be carried out in the next lecture. In this lecture, we have determined the magnitude and direction of the reaction force, assuming radius and ulna as a single bone. In the next lecture, the joint reaction forces will be calculated separately for humeroradial and humeroulnar articulations. The references based on which the lecture has been prepared are listed here. Thank you for listening.